Welcome to the Deep Dive, your shortcut to being well-informed. Today, I want you to imagine something pretty incredible. Picture a computer not just spitting out an answer, but actually showing you how it got there,
Hmm.
laying out its whole thinking process, step by step. That world, the world of AI reasoning, it's just exploding right now. It's transforming what we thought large language models, LLMs, could actually do.
It really is a remarkable shift, yeah. We're definitely moving beyond just basic chatbots generating text. These models are starting to, well, think, to problem solve in some really complex ways, make informed decisions even.
And that's exactly our mission today. We're taking a deep dive into how LLMs are pulling this off, how they're learning to reason.
Mm.
We want to demystify the latest breakthroughs, look at the core strategies behind this evolving intelligence, and maybe uncover some surprising facts about how we're teaching AI to think.
Absolutely. And if you've ever felt a bit, swamped by all the AI information out there, this deep dive is really for you. We're aiming for those aha moments, showing you not just what's happening, but crucially, why it matters for the future of AI and, well, for you.
Okay, so let's unpack this a bit. We talk a lot about LLMs generating text, but what does reasoning actually mean in this context? It's got to be more than just talking, right? For us, reasoning is like fundamental cognitive stuff, analyzing evidence, building arguments, using logic, reaching conclusions. How does that map onto an AI?
It's interesting because the ambition is pretty much the same. For LLMs, reasoning is what really separates the sophisticated systems from your basic pattern matching chatbots. It's what nudges them closer to that big goal of artificial general intelligence, AGI. The real shift is it's not just about the final answer anymore. It's about the LLM generating its thinking process, that clear trail from question through logical steps right at the answer.
Right, so it's the journey, the how, not just the what. That feels like a fundamental change in how we even interact with these models.
Yeah.
What do you think really kicked off this surge in AI reasoning research? Was there like a specific moment or breakthrough where everyone went, okay, wow, LLMs can actually think?
Oh, definitely. Things really started accelerating around 2022. That year was key. We saw two major developments: the introduction of chain of thought prompting, or COT, and of course, the public release of ChatGPT. These weren't just small steps. They really highlighted the incredible potential for LLMs to scale their reasoning abilities in a way we just hadn't seen before.
Okay, Coty and ChatGPT, the sparks that lit the fire. Got it. Now, this field is moving fast, it's diverse. To help us get a handle on it, our sources lay out a really useful framework. They talk about organizing LLM reasoning along two sort of distinct lines: regimes and architectures. Think of them as two ways to look at how AI is learning to think.
Exactly. It's a good way to structure it. Regimes basically asks when the reasoning happens, is it during the test itself, or is it something learned during training? And architectures looks at what parts are involved. Is it just a single LLM working alone, or is it a more complex system, maybe involving tools or other agents? This kind of two-dimensional view really helps map out all the different research paths.
All right, let's tackle that first dimension. Reasoning regimes. Inference versus learning. First up is inference scaling. You called it thinking on the fly earlier, which I like. What does that actually involve for the LLM?
Thinking on the fly or inference scaling, yeah, it's about boosting an LLM's reasoning during the actual test time. And the key thing is this happens without tinkering with the model's underlying parameters. It's core programming. It's essentially like giving the model more time to deliberate, to explore different paths to a solution before it gives an answer. Kind of like how we might pause and really think through a tricky problem.
And apparently, this is really powerful stuff. Some 2024 research suggests that doing this well, scaling this test time thinking, can actually be more effective than just making the models bigger. That's kind of counterintuitive, right? The way it thinks matters more than just its raw size sometimes. So how do they actually engineer this? How do you make it think better on the fly?
A lot of it boils down to crafting prompts that specifically provoke reasoning. Chain of thought, or COTI prompting, is the classic example. Back in 2022, researchers found that just adding simple phrases like, let us think step by step, could dramatically boost reasoning accuracy. And then there's zero-shot copy, which is even simpler. It gets similar results without needing any specific examples in the prompt.
It's almost like finding a magic phrase, isn't it? Just a few words unlock so much potential. Makes you wonder what other simple tricks are out there.
It does, and there are other techniques too. Demonstration engineering, for instance, involves giving the LLM relevant examples to learn from, almost like learning by analogy. Some methods even use hundreds or thousands of examples. They call it many-shot in context learning. And then it gets really meta with prompt optimization, where you actually use LLMs to automatically generate and refine other prompts, things like the automatic prompt engineer, APE, or genetic prompt search, GPS.
Whoa, AI optimizing its own instructions.
Okay.
So that handles the input side. But how do they optimize the output during this thinking on the fly?
Good question. That's where search and planning techniques come into play. Some methods focus on generating reasoning subtasks, breaking down big, complex problems into smaller, more manageable steps, much like humans do. Others, like tree of thoughts or the newer graph of thoughts, actually let the model explore multiple potential reasoning paths at the same time.
So it's like the LLM is actively brainstorming, trying out different routes instead of just going down the first one it finds. And we saw a big example of this recently, didn't we? OpenAI's O1 model back in September 2024.
Exactly. O1 was a key milestone. OpenAI showed its performance consistently improves with more time spent thinking. It really validated this whole idea of inference time computation being powerful for complex stuff like math, coding, and science problems. A clear win for the inference scaling idea.
Okay, so we've covered thinking on the fly, unlocking reasoning right when it's needed. But what about the other side? What if you could kind of build that reasoning ability right into the model from the start? That seems to be the idea behind learning to reason or training for deliberate thought.
That's precisely it. Instead of relying purely on runtime calculations, this approach is all about improving reasoning capabilities through dedicated training. The goal is to embed these reasoning skills directly into the LLM's core structure.
I'm guessing that's not easy, though. Training sounds like it would need a lot of data, right?
Yeah.
Like really high-quality, step-by-step examples of human reasoning.
That's the main bottleneck, yes. Getting that kind of data, human-annotated step-by-step reasoning, is incredibly expensive and time-consuming. So what researchers are trying to do is figure out how to automatically generate these reasoning paths or trajectories. And then they use different training strategies on that generated data. Things like supervised fine-tuning, SFT, on datasets that already have long chain-of-thought examples, or preference learning, which essentially teaches the model to tell good reasoning paths from bad ones. Methods like DPO, direct preference optimization, fall under this. And then there's reinforcement learning, RL, which is really powerful because it lets the model learn complex strategies and behaviors without needing explicit step-by-step labels for everything.
RL sounds fascinating, the model learning through trial and error, almost. And this brings us to another big model, DeepSeek R1 from January 2025.
Yes, DeepSeek R1 made waves. It's an open source model, and it achieved performance pretty close to OpenAI's O1, but using significantly less computational power during training. What was really striking was their finding about the emergence of sophisticated behaviors such as reflection coming directly from the RL training. This means the model wasn't just following steps, it learned to spontaneously reevaluate its own reasoning process. That's a big deal.
Reflection. Wow. That feels like a major step towards something more human-like, maybe. Okay, so we've covered the when of reasoning, inference versus learning. Now let's pivot to the how, the system architectures. Standalone versus agentic, a standalone LLM system. It's probably what most people think of, right? Just one AI model doing its thing.
That's the basic setup, yeah. A single LLM takes an input, produces an output, maybe explaining its reasoning along the way. All its decisions are based purely on its internal knowledge or what it can figure out by repeatedly querying itself. It's like a self-contained thinker.
But then things get more complex with agentic systems. It sounds like where LLMs start to get, well, help from tools, maybe other AIs.
Exactly. This is a major shift. Agentic systems introduce two key capabilities: interactiveness, the ability to engage with the outside world, and autonomy, the ability to initiate and carry out actions independently. It moves the LLM beyond just being a brain in a vat, so to speak.
Okay, and within agentic systems, the first type is single agent systems. So still one LLM, but now it can use external tools. Like what?
Right. It can interact with things in its environment to help its reasoning. These tools could be anything: databases for knowledge, code interpreters for calculations, maybe even access to calendars, maps, web search, you name it.
So it's not limited to just what it was trained on. It can look things up, check its work.
Precisely. It dynamically uses these resources to make better decisions. We see common patterns here, like the generator-evaluator pattern. One part generates an action or a piece of reasoning, and another part, maybe a fact-checker or a code compiler, provides feedback. Though this can lead to something called reward hacking, which is quite interesting.
Reward hacking, what's that?
It's where the LLM gets clever about achieving the goal, the reward, but maybe not in the way intended. It finds loopholes or shortcuts, kind of like a student gaming the test rather than learning the material. It's a real challenge in training these systems.
Huh. Okay, I can see that happening. And there's another pattern. Generator, critic, refiner.
Yes. Here, you have a reasoner proposing an action, a critic identifying specific flaws or errors in that proposal, and then a refiner revising the action based on the critique. The tricky part here can be over-refinement, where too much back and forth actually makes the output worse, not better. Finding that balance is key.
Makes sense.
Right.
But these single-agent systems are already achieving impressive things, right? Like Grok 3 Deep Search and OpenAI Deep Research from early 2025.
Absolutely. Those systems show how these agents can, quote, independently discover, reason about, and consolidate insights from across the web. They're doing complex information retrieval, using tools like code interpreters for analysis. It really demonstrates the power of combining LLMs with the external world.
Okay, so one LLM plus tools is powerful. What about multi-agent systems? Is that literally multiple AIs working together?
That's the next level, yeah. Here you have multiple LLM agents actually communicating and interacting with each other, often before they even interact with the external environment. Each agent might take on a specific role, like in a team.
Wow. Okay, I can immediately see the coordination problems there. Getting them to talk effectively, agree on a plan, sounds like managing a human project team.
It has similar challenges. Designing good communication protocols is crucial. Should they collaborate? Should they debate? Maybe taking adversarial roles? How do they reach a consensus? We see patterns emerge like the debate pattern, where agents argue different points of view to arrive at a stronger conclusion, or the reconcile pattern, where they engage in collaborative discussion and maybe use something like confidence-weighted voting to agree.
That's fascinating. And there are actual products using this now, like the Manus agent.
Yes, Manus Agent is often cited as a prominent example, showcasing what these multi-agent systems can achieve in practice. It highlights the potential when you get multiple specialized agents working in concert.
It's really interesting, though, how our sources bring it back to a common idea, regardless of whether it's inference or training, standalone, or agentic. It seems to always come down to managing inputs and outputs effectively.
That's a great way to put it. It provides a unifying lens. For a standalone LLM, it's about crafting good prompts, input, and refining the generated text output. For a single agent, it's about getting useful perceptions from the environment, input, and executing precise actions, output. And for multi-agent systems, it's all about designing clear communication between agents, input, output, and enabling effective coordination towards a goal, output. It really is the nervous system connecting all these approaches.
Right. Okay, so as these systems get more capable, we're seeing a trend you mentioned earlier, moving beyond generalists towards domain-specific reasoners. That makes sense, right? Sometimes you need an expert, not just a jack of all trades, especially for really tough areas like math and coding.
Exactly. While AGI is the ultimate goal for some, right now the state-of-the-art is often found in models specialized for specific, complex domains. Mathematical reasoning is a huge one. There are broadly two approaches. The informal approach treats math problems kind of like natural language puzzles. Models like DeepSeek Math and MetaMath are examples. They use vast amounts of math text in their training, plus techniques like tree search for exploring solutions and integrating external tools, maybe like a calculator or a symbolic math engine. And they're getting really good results on benchmarks like GSM-8K, even up to competition-level problems like AMO.
Treating math like language.
Mm-hmm.
Interesting. There's also a formal approach.
Yeah.
Sounds more rigorous.
It is. This approach grounds the reasoning in very precise symbolic logic systems, often using tools called proof assistants like Lean. The big advantage here is that you can automatically verify if each step of the reasoning is logically sound. We've seen breakthroughs like alpha proof and alpha geometry. Alpha geometry famously solved Olympic-level geometry problems by combining neural networks with this kind of symbolic verification.
Olympic-level geometry, that's just incredible. And the other big domain is code generation. Code itself is basically a formal language for reasoning, right?
Absolutely. And the progress here has been just as dramatic. We've gone from generating small code snippets to tackling complex competition-level programming challenges like Google DeepMind's AlphaCode did back in 2022.
And where are we now with coding AI?
The current cutting edge involves models like DeepSeek R1 again and OpenAI's O3. They're often using end-to-end reinforcement learning specifically tuned for code generation. The real-world impact is becoming clearer too. We're seeing benchmarks like SWO Bench, which stands for Software Engineering Benchmark. It challenges LLMs to fix real bugs found in GitHub repositories. This requires really deep logical reasoning to understand the existing code, find the flaw, and implement a correct fix. It's pushing towards automated software engineering.
Fixing real GitHub bugs.
Yeah.
Okay, that's impressive. This is all moving so fast, the progress is undeniable. But as always, there are big hurdles. Let's talk about the road ahead, the major open challenges in LLM reasoning. What are the big sticking points?
Well, despite all the progress, there are definitely significant challenges. A major one is what our sources call the evaluation enigma. Basically, how do we know if an AI is genuinely reasoning correctly? We tend to judge them by the final answer, but getting the right answer doesn't automatically mean the logic used to get there was sound.
All right, it could just get lucky or use flawed logic that happened to work for that specific problem.
Exactly.
Yeah.
Research has shown LLMs can produce what are called unfaithful reasoning chains. They get the right result for the wrong reasons. And there's a kind of catch-22 here, too. As the reasoning tasks get harder, evaluating them becomes incredibly difficult, sometimes even for our best AI models. The source material puts it well. If a model cannot perform a task, how can it judge if the task is done correctly?
Hmm. That's a really tricky problem, almost a philosophical one. So we desperately need better ways to evaluate the process of reasoning, not just the outcome. We need to check for coherence, factual accuracy, logical flow.
We do. And this ties directly into the next big question, understanding reasoning. Is it thinking or just super imitation? When an LLM produces that step-by-step output, is it genuinely reflecting an internal thought process? Or is it just mimicking complex patterns it saw in its massive training data?
Yeah, that's the multi-billion-dollar question, isn't it? What does intelligence actually mean here? I know some qualitative analyses, like one on GPT-4, have been quite critical, suggesting that despite impressive performance sometimes, it still remains incapable of true reasoning.
That's right. And empirical studies back this up to some extent. They often show that LLMs struggle to generalize their reasoning skills to new situations they haven't seen before. This suggests they might be relying more on learned, specialized procedures rather than a flexible, general intelligence. Formal analyses have also suggested that LLMs often default to retrieving stored knowledge rather than engaging in genuine novel proof planning or logical deduction.
Knowledge retrieval versus actual reasoning. That's a critical difference.
Yeah.
Okay, and the final big challenge seems to be about fuel, the data dilemma.
Yes, absolutely. To train these state-of-the-art reasoning systems, especially the ones using reinforcement learning, you need huge amounts of high-quality data. We're talking about challenging problems paired with reliable, verifiable outcomes or reasoning steps. The issue is we might be hitting the limits of easily available human-generated data, especially for complex, open-ended tasks or agentic scenarios where defining the ground truth is really hard.
So we need more fuel for the engine, but the fuel is getting scarce and expensive to create.
That's a good analogy. And it connects to reward model challenges too. Training models that can accurately judge the quality of each step in a reasoning process, assoggeante process reward models, is vital for reducing things like hallucination and ensuring logical consistency. But creating the data for these reward models, which requires detailed step-by-step human feedback, is extremely expensive. Automated methods are being explored, but they often struggle to generalize well to new types of problems.
Wow, what a journey we've really taken today, diving into this whole landscape of LLM reasoning. We've seen this incredible evolution, right? From just following simple instructions to tackling really complex multi-step problems. We explored that dance between thinking on the fly with inference scaling and learning to think through dedicated training. And her LLMs are morphing from these standalone thinkers into powerful agentic systems with tools, even working in teams. I mean, conquering complex math, debugging real-world code. These aren't small things. They're genuinely reshaping our tech future.
It's truly fascinating. And as these LLMs get better, master more complex tasks, even show glimmers of things like self-reflection, it really forces us to ask that profound question, doesn't it? Are we actually witnessing true reasoning, true understanding emerge? Or is it just an incredibly sophisticated, almost uncanny form of imitation? And maybe the even harder question is, what will it take for us to confidently tell the difference? And perhaps, what will it take for these systems to develop a truly generalizable intelligence, one that can surprise us with genuine, innate ingenuity? This deep dive into the AI mind is definitely far from over, and the questions are just getting bigger and more intriguing.